In the previous video, we evaluated a few different examples of expressions involving unions, intersections, and complements, and noticed something interesting. Specifically in that example, the complement of A union B was equal to 0.689, and A complement intersect B complement was equal to the same. Also, the complement of A intersect B was identical to A complement union B complement. As I mentioned in that video, this is not a coincidence. In fact, this relationship will always be true and is important enough in the history of mathematics that we actually give it a special name, De Morgan's laws, named after a British mathematician from the 19th century. Now, I'm no math historian, but I do believe this was an idea that was well known since the time of Aristotle, well before the 19th century. But its name is dedicated to De Morgan because of his contribution to formalizing it within modern logic. And if you study logic, you'll see this show up again and will be particularly useful there. But at least in context of our discussion in set theory, these laws boil down to two statements. Number one, the complement of a union of sets is the intersection of their complements. This is why part A and C were equivalent, and we can write this symbolically as the complement of A union B equal to A complement intersect B complement. Number two, the complement of an intersection of sets is the union of their complements. This is why part B and D were equivalent, written symbolically as the complement of A intersect B is equal to A complement union B complement. Again, this is always going to be true, regardless of the specific sets A and B, so we can just label them arbitrarily. Now, with that said, perhaps you're wondering if there exists, or maybe you're even attempting to come up with some kind of extreme case to break this. If so, excellent. As this is a great instinct for anyone learning math, try to find ways in which you can break the statements that you've been given. But you won't find one in this case. This one we can prove. We'll let this rectangle represent our universe, and each of these two circles represent some arbitrary set A and some arbitrary set B. And let's copy this and hold on to it as well. Now, I'm going to draw them like this, but these could really be anything within the universe. They could be big sets, small sets, overlapping sets, disjoint sets. It won't change our proof and the result that we get. So let's take a look at the expressions that we have and see if we can use the Venn diagrams to represent them. First, let's examine the complement of A union B. Keeping in mind our order of operations, we first need to find A union B, which is this blue region here. Then, the complement of that will be everything that is not blue. Let's color that in green. Now let's examine A complement intersect B complement. Again, we'll need to follow our order of operations here and begin with the complements. Let's color in the region of A complement blue and then the region of B complement in yellow. Their intersection then is represented by the region where the blue section and the yellow section overlap. Coloring this green, we see that both of the pictures, the one on the right and the one on the left, have the same green region. This demonstrates visually that the complement of A union B, represented in green on the left, is equal to A complement intersect B complement, represented in green on the right, and this is true for any sets A and B that we might draw. We can do something similar for the second statement of the law as well. Here, the diagram on the left represents the complement of A intersect B, and the one on the right represents A complement union B complement. We can see again the green regions are the same in each, thus so are the two expressions. One final thing that we can consider here is that this isn't just true for a pair of sets, but holds for any number of sets. We could take the union of 100 sets if we wanted, then take the complement of that, and it would be equal to the intersection of all of the complements of those 100 sets. So let's express the law a little more generally to account for the fact that this works for any arbitrary number of sets. And so let's assume we have a list of sets. We can label them with subscripts, so maybe A1, A2, A3, and so on for however many that we have. We can use a variable to represent this. So we'll write something like AN to represent n number of sets, for however many that does end up being. If n was 3, for example, we'd have A1, A2, A3 for our list. If n was 5, we'd have A1, A2, A3, A4, and A5 for our list, and so on. Then, to represent the union of all of these sets, we'll write a large U and an AI, then writing a small I is equal to 1 below the union symbol and a small n above it. This is to signify that we're taking the list of all of the A's from 1 to n. So for example, the union from I equals 1 to 3 would be A1 union A2 union A3. We can write a similar notation for intersections as well, just flipping this sign upside down. And so then we can express De Morgan's law as the complement of the union from I equals 1 to n of AI equal to the intersection from I equals 1 to n of AI complement. We can write the second statement of De Morgan's law similarly. And so now, with a proof and a generalization of the statement, this about sums it up for De Morgan's laws in context of set theory, though be prepared to see them again in a study of logic, where they will be helpful to simplify logical expressions. For now, I hope you found this video helpful, and do let me know in the comments below if you have any questions. Otherwise, have a great rest of your day.